All right, y'all, today we're going to be talking about the second fundamental theorem of calculus and what we call the average value of an integral function. So the second fundamental theorem of calculus, besides being almost as important as the fundamental theorem of calculus, tells us that for f, a continuous function on an open interval I, which is just an interval, and a, any point in I, and states that if f is defined by the integral, so remember capital F usually represents our integral, regular f represents our function. And states that if f is defined by the integral, the antiderivative, then the derivative of the integral from a to some function f of x of f of t times dt is equal to f of x times f prime of x. Okay, now that is a lot of words. Okay, and it's very difficult and wordy. So we're going to actually look at an example before I kind of explain this a little bit more, because me trying to explain it to you is not going to make any sense right now until we actually do an example. And just missing our little derivative in the wrong spot. All right, so there are three steps to the second fundamental theorem of calculus. We're going to integrate the function. We're going to plug in f of x for b and f of b minus f of a, and then we're going to derive. So really what it's telling us to do is to integrate and then derive. So we have the integral from 0 to x of t plus 2 dt. So the first thing we're going to do is we're going to integrate. Okay, so our integral of t plus 2 dt is t squared over 2 plus 2t. And we're evaluating it from 0 to x. Okay? So then we're going to plug in x for f of b. So this is going to be x squared over 2 plus 2x. And then minus, of course, if I plugged in 0, the whole thing would just be 0. So we get x squared over 2 plus 2x. Then I'm going to derive my answer. So my answer would be 2x over 2 plus 2. And I'm going to multiply all of this. So it's a little hard to see, but this f prime of x is just the derivative of this f of x portion. So the derivative of x on this example here is just 1. So I multiply by my derivative of x, which is just 1. So my final answer would just be 2x over 2 is x, and then plus 2. Okay, now I want you to notice some things. Okay, compare x plus 2 to our original problem, our original function of just t plus 2. What does it look like? We really did it. Well, it really looks like all we did is plug in that x. We just did t plus 2. Okay, plug in x. New equation is x plus 2. Okay, so you're probably thinking, Mr. Arbone, why did I have to integrate and then derive? Well, the whole point of the second fundamental theorem is that integrals and derivatives are that opposite relation to each other. So they should end up canceling each other out. So when we're doing this integral from 0 to some function f of x, our final answer is really just going to look like if we plug that f of x into whatever is inside the integral. Okay? That's what it's supposed to do. That's what's supposed to happen. So it is supposed to be just that easy. Now, the top of your integral is not always going to be x. It can be a little bit more involved of a function like x squared, x cubed, sine of x, anything like that. Okay, so we just have to make sure that we do multiply by the derivative of that top function. So if it's just x, it's just going to be 1, so it's not going to have any other bearing. But if it's something greater than x, then it'll be something other than 1. And so then you will multiply by it, and it will change the function just a little bit. So let's try number 13. But instead of doing it the long way, we're just going to apply the formula. Okay, so the formula says all we do is we plug in our f of x. So we plug in this x squared into everywhere where I have t inside. So this becomes x squared squared minus 1. And then the second part of the formula is that I multiply by the derivative of f of x. I multiply by the derivative of that b part of my integral. So the derivative of x squared would be 2x. And of course, if it's a free response question, you could leave it like this, but second fundamentals are pretty much always going to show up as a multiple choice question. So we do want to simplify it just a bit. So x squared squared is x to the 4th, and then minus 1, and we're still multiplying by 2x. So then multiply by 2x, distribute it to everything on the inside, and we get as a final answer 2x to the 5th minus 2x. And that is all you have to do for your second fundamental theorem. Super easy. Now, one thing I'll caution you on, second fundamental is one of those things that's so simple and easy that it's easily forgotten. Okay, so just make sure when you see that derivative of the integral and there's t's and x's and everything involved, it's second fundamental. You just need to apply the formula. Super, super simple. This should be a 15, 20-second problem on the AP exam. So let's go look at another example. Let's look at 14. Okay, find the derivative of f of x is equal to the integral from pi over 2 to x cubed cosine of t dt. So this one, they didn't write the full formula out where it's the derivative of the integral. They just said find the derivative of f of x, which is equal to the integral. So they're still telling you to derive the integral. They're just writing it a little different. Okay, so we're going to apply our formula. So cosine of x, so cosine of x cubed, and then I multiply by the derivative of x cubed, which would be 3x squared. So my final answer would just be 3x squared cosine of x cubed. Nice and simple. Okay, now one thing you might notice a little different, and you're probably thinking, well, Mr. Abone, what about that pi over 2? Okay, notice that nowhere in my formula does it ever mention a. Okay, and the reason for that is because a is a constant, it's some number. And what am I doing? I'm integrating where I'm going to plug in a, and then I'm deriving where any constants that are being added or subtracted in the problem are just going to go away. So the reason why I can ignore whatever's in the bottom of that integral is because when I derive it, whatever that number is just going to go away. So whatever I plug in for the second half of my f of b minus f of a, I'm going to get a big old number for it, and it's just going to go away and become 0. Okay, so we get to ignore the bottom piece as long as it's not another function. If it's another function, like say that was x, then we wouldn't get to ignore it. But you won't really see that in AB, so don't worry about it. Okay, and as a final kind of statement, the second fundamental theorem of calculus draws the conclusion that when a function is continuous, it must have an antiderivative. So it's basically just saying that if I can derive and integrate, these things have to be true. That's what the second fundamental theorem says, essentially, is that if I can integrate, I have to be able to derive. I can go back and forth, continuous functions, all that kind of good stuff. Okay, the second piece we're going to look at is what we call the average value of a function. So the average value of a function is a special equation used to solve for the average value over a derivative. It is the integral version of our average rate of change. Okay, so remember, average rate of change was your f of b minus f of a over b minus a. We used it to find like the average rate of change if you had the position function and I wanted to find the average velocity. Well, now average value is if I still want to find that average velocity, but I have the velocity equation. So same end result as average rate of change, different function being started with. So the average value of a function f of c is equal to 1 over b minus a times that integral from a to b of f of x dx. So the only extra thing we're adding an extra average value is this 1 over b minus a. So all I'm doing is I'm dividing the entire area by whatever the distance is. And so what's that going to do is it's going to find me what is the average value on that curve over the length of it. So it's going to kind of equalize out that average or that total value of the area under the curve by dividing it by the distance. And it's going to find that average y value that I travel on that exact curve. So let's look at an example. So 15, We want to find the average value of f of x is equal to 3x squared minus 2x on the interval 1 to 4. So this is going to be equal to 1 over b minus a, so 1 over 4 minus 1, times the integral from 1 to 4 of 3x squared minus 2x dx. Okay, so 1 over 4 minus 1, that just becomes 1/3. Integral from 1 to 4 of 3x squared minus 2x dx. Now I can integrate, so this becomes 1/3 times x cubed minus x squared. I'm evaluating it from 1 to 4. So notice the 1/3 is all the way on the outside. So I'm going to really multiply by the 1/3 as my last step. I'm not multiplying it into the function to make it more difficult. Okay, so 1/3, 4 cubed minus 4 squared, minus 1 cubed minus 1 squared. Okay, 1 cubed and 1 squared, that's just going to cancel each other out. Okay, so 4 cubed is 64 minus 16, which would be equal to 48. So this becomes 48 times 1/3, which would just be 48 over 3. So to put it in perspective, 48 was the area under the curve 3x squared minus 2x. 48 over 3 is the average value of that function on the interval 1 to 4. Okay, so it has values higher than 48. It has values lower than 48, but the average value on the interval 1 to 4 would be 48/3. Okay, so just kind of something interesting to think about with average value. It's another way to find that average. And when you get to the AP exam, they're going to expect you to be able to pull both of them out when you need to. Depending on what function you have, when it asks you to find the average, you'll either use average value or you'll use average rate of change. It just depends on what function you have. Average rate of change is if you have like the original function and you want to find the average rate of change on the derivative. Okay, average value is if you have that derivative and you want to find the average on that derivative or on that function. Okay, so let's look at one more example with trig. So number 16, find the average value of f of x is equal to cosine of x over the interval 0 to pi over 2. Okay, so same thing, just with trig. So 1 over pi over 2 minus 0, interval from 0 to pi over 2 of cosine of x dx. So that's going to be equal to pi over 2 minus 0 is just pi over 2. 1 over pi over 2 is the same as 2 over pi. So 2 over pi times integral of cosine of x is sine of x. And I'm evaluating it from 0 to pi over 2. So this becomes 2 over pi times sine of pi over 2 minus sine of 0, which is equal to 2 over pi times 1 minus 0, which 1 minus 0 is just 1. So 2 over pi times 1 is just equal to 2 over pi. And that's your final answer. So once again, 1 is the value under the curve, the entire curve, cosine of x from 0 to pi over 2. Value under the curve, area under the curve is 1. 2 over pi is the average value of the function cosine of x on the interval 0 to pi over 2. So it's really important as we get to this point in calculus, y'all, that we understand what everything means. What are we actually finding when we're applying these rules? Because for your response question, it's going to ask you to find something, and you're going to have to know what rule to use. So if you know what rules are used for what, it's going to make those for your response questions easier. But that is second fundamental theorem, y'all, and average value. If you haven't already, you can go ahead and start working on that practice and finish up your fundamental theorem practice. All right, thank you.